Okay, so it's a pleasure to introduce our first speaker this morning. Tobias Ekholm is back for his third talk on higher genus curves and topological recursion.
Thank you. So I will start by talking about what was sort of left over yesterday. So I'll talk a little bit about the same story as yesterday, but for knots in other manifolds. And then I will try to describe the rest of the story, which is, to be honest, more maybe research program than actual results. But anyway, I think it's interesting, and I think it explains some of what's going on. So I'll do that. But let's first try to remember what we did yesterday. So the upshot was that we start with a knot in S3, and we take its conormal. We shift it off the zero section, then we can go through the conifold transition. So this x is O minus 1 plus O minus 1 over P1. And in there can be actually holomorphic curves forming on this non-exact Lagrangian. And in particular, we can talk about the Gromov-Witten disk potential. And I talked a little bit about how one needs, how one could define it using these bounding chains, etc., etc. But the upshot is that if it, whatever way it is defined, then this will be a local parameterization of what we call the augmentation variety, which in turn, in terms of this knot contact homology at infinity, can just be computed by solving an algebraic equation. So in some sense we get, after the fact, basically the idea is that we are probing the holomorphic curve theory inside this slightly difficult case in the conifold by looking at infinity, where we have more control over what's going on. Okay, so and the proof used Foucault and company's idea with bounding chains, and this is a kind of schematic picture of what's going on, where we have the chain map. The SFT augmentation argument, which is what I'm calling counting holomorphic curves, asymptotic to ray ports at infinity and then stretching down along the Lagrangian field. It doesn't quite work, but it can be made to work if we include these bounding chains, and the actual equation of the augmentation variety comes from counting the insertions at infinity. So somehow these up there, and the curves here, they appear very simply. They just wrap around one generator. We can keep track of how to count them. So these will be also part of our SFT later. But let's now start by talking a little bit about other manifolds. So in this case, we have from point of view of what we were doing, we sort of think of this as taking T star S3, take a lot of branes on the zero section and collapse them, and so basically what you do is you take T star S3, and then you remove the zero section, and you put some kind of symplectic area on the fiber S2, right? And from point of view of holomorphic curves, this looks extremely bad. You have a lot of symplectic surfaces floating around down at minus infinity, so it's not the dream situation. But luckily, we can compactify the whole picture by adding this P1 in the middle, and you get O minus 1 plus O minus 1. So then you can make sense of the holomorphic curve theory in this setup. And up to that point, of course, you can do the same thing in any three manifold. You put some symplectic area here. Now we can ask the question, when can you compactify things to get a nice holomorphic curve theory? And here what we're saying is that if you have a geometric quotient of S3, or for me at least, when you have RP3, you can do it. And the upshot is that for these spaces there should be one scalar parameter. So here it is for each free homotopy class. So here we have this CP1 area, so that's the scalar parameter of the trivial homotopy class, right? So there's actually no loops at all, but there is a trivial class.
Does this use the fact, that the geodesic flow is periodic?
Probably, I mean, you sort of take you make a quotient of the conifold in some sense, right? So you extend the group action. But yeah, I don't know. I mean,
Particular symplectic cut.
yes,
But that doesn't. Then you have to collapse it.
maybe. Yeah, I don't know, but it may well be. I didn't kind of think too much about this, but just in kind of simply said it. But anyway, so when we can do it, the idea is that out at infinity, we should still have the unit cotangent bundle of M, right? So we haven't really changed the geometry out at infinity. It looks exactly up to then this one, which is some finite area out at infinity, becomes small, so it should just mimic the U star M geometry. And now we would like again to probe things from infinity, but in this case we cannot completely, as we did with S3, just pretend it's R3 and forget about closed orbits. In this case we have to do something slightly different. So let me draw the picture. So what we want to do is we want to study this DGA type of thing, where the differential looks like that. So you have Rave chords here. But now, when you look at the one-dimensional moduli space, you know what could actually happen is that you start developing something like this, and you break off holomorphic plane. So the dimension here, they're now kind of rigid inside, or maybe they're not so rigid. They're degree 1, and this is degree 1, so I should have this in degree 2. So basically what we're seeing is that we need to consider, we can somehow save the day if we also add the orbits as variables, which means in this language that the Sondrian DJ generated by chords will be an algebra over a similar contact homology algebra generated by orbits. So in the S3 case we can forget about it because somehow the smallest degree there is 2, so if you look at the 0 degree chord, then you don't need to care. But here we do need to care, so there will be something degree 0. And in fact, we will care again only about the degree 0 piece because we're interested in augmentation, and so we need to understand what is the degree. So again, I should say. The Rave orbit, so before we had chords stretching from the knot to itself, and they were binormal geodesics, and now we have closed geodesics which correspond to Rave orbits. And again, the index in our algebra, the kind of Conley center index, is the Morse index of these things. So you see again that for the algebra, the degrees of generators is 0, 1, 2, and so nothing in negative degrees, so it's a kind of pretty good situation. And so we need to look at the degree 0 port. And in fact, it turns out that it's exactly what we would like it to be. So it's exactly the free algebra, the commutative, generated by the free homotopy classes. So yeah, one can see this. So I'm not going to waste too much time on this argument, but basically you can see it by using the standard isomorphism map on, say, S1 equivariant symplectic homology down to geodesics, and then you find that on the linearized level, so you're just forgetting about higher products. So on the linearized level, you have something in degree 0, nothing in degree 1, and then something in degree 2. But we can compute the full DGA by somehow a spectral sequence starting from the linear story, then taking the quadratic and higher. But you see, because of degree reason, if there is nothing in degree 1, you can have no differential where the outputs are all degree 0, right? It's somehow, there's nothing rigid here. So there's somehow no constraint, and therefore you get this algebra. Okay, very good. So in other words, when we now try to work in this U star u star m, we take the conormal lambda k, and we take its algebra. Now we get an algebra over the torus, the H1 generator, so the torus, and then we have all the homotopy classes, which here are identified with orbits, generating the algebra of orbits, except for one for the trivial class, which again is a cube, right? So this again is this homology class of the fiber sphere. And so, so again, we would get by exactly the same argument, we get we can now sort of compute the disk potential by exactly the same means, but we need to know what are the gammas, right? So and what are the gammas? In this case, you have the orbit, and now we're going into this what I called XM, which was the counterpart of the coniphone, and then we need to count such holomorphic curves. It's like a Gromov potential with positive ends as well, right? So for each gamma, there is some function in terms of the actual Kähler parameters, which counts the curves with a positive function at gamma, and that's exactly what should go into this equation. And once we know all these things, and then we can compute the Gromov potential of the of LK by the same type formula. And let's look at some examples. So they're kind of basic examples. So I'm claiming that somehow we can actually, for at least for simple things like length spaces, we should be able to do this. So in particular in RP3, how would the calculation go? So remember how it went in S3. We take any knot, we braid it around the unknot, and then we look at this degeneration. So we degenerate the knot towards the unknot, and we get the kind of subdivision into big disks and small flow trees. And in RP3, you can braid anything around the line, and the basic calculation is therefore for the line. So for RP3 again, so this XM is P1 times P1. There are various ways to see that you can compactify like that, but let me leave it. At least you see it's two Kähler parameters. And when you do the calculation, the augmentation polynomial, you get the following answer. So here this is the former cube, and gamma is the new variable. And that somehow matches with mirror symmetry calculations. Yeah. Maybe I'll come back to this next time. But basically, you see that once we have this calculation, so what I'm actually claiming is that I should say one thing. So as before for the unknot, we need to sort of draw this one new ingredient, which I need to say something about. So if this is S3, then somehow RP3 is here. And you take the line, and the line lifts to half of the unknot, right? And now, when you take the conormal, remember that basically we did do some kind of calculations where some rate, this is the rate chord of the unknot, and it's sort of flowing this way and flowing the other way, so you have the same, basically you have the same four disks as before. Now this is, if I draw it as an equator, it's a longer chord, but it can shrink this way, and you get somehow, you got two disks by when it gets there, because you go there. So then these are the first, basically the same terms as for the unknot. But then there is one more term, and that's the term that comes from, if you think about this exactly as you're suggesting about this, nice round geodesic flow, then there is a holomorphic curve which somehow goes from a chord to an orbit. Right? And that's exactly when you take somehow the minimum orbit in this family, then it's sort of Baltimore situation. That's how this term arises in this calculation. And one can now kind of speculate about what should be going on in other spaces and so on, but let me know. So at any rate, I think this would be great to understand, and I think that basically for calculational purposes, you can do many things, both here and in other land spaces. But let me now move on to the little bit less well-established part of the story. So in some sense, from the physics perspective, what we're getting, we have this augmentation variety, and we would like to somehow quantize it. And what I'm describing is what should correspond to this quantization on the not contact homology part. And so what one should do here is that, we're dreaming that we can do omnipotent and don't have any kind of mathematical problems. So then, we would like to have a theory which involves, at infinity, involves counting curves that are, complicated. So they have several boundary components, several positive and negative punctures, and we would like to count them just like we counted these curves. So the main thing for defining this not contact homology was that the boundary of one-dimensional moduli spaces look like this. Or if you want to, in order to find augmentations, the corresponding boundary equation look like that, right? So you have some R invariant thing and then this constant, the rigid curves inside. So we would like to dream up a theory which does the same thing for arbitrary curves with arbitrary boundary on lambda k times r, and then kind of stretching down with some other curves inside with also maybe complicated curves which lies on Lk, and they have all the dimension 0, this dimension. So that's what we would like, and it's difficult because we are now fighting even more than before with this boundary splitting. So before we could split off disks, but there's sort of one moving part and some stationary part that we split off. Now there is no such thing. So it can somehow, when you have genus inside or several positive punctures, it can self-split, and so we have to work a little bit harder. But before we go to work, let's continue dreaming a little bit and see what would be the structure of such a theory. So there is such theory sort of known in symplectic field theory when you have just orbits, but not so much with Lagrangian boundary conditions, so it's more difficult. So, but what we would have is so we are again back in this S3 case, so I don't want to discuss more complicated yet. So we would have somehow an SFT potential that counts all the rigid curves inside the manifold with boundary on Lk. And what does it mean? So it means that we have to count curves with, as drawn over there, with several positive punctures, possibly with genus, and so on. Right? So that's what it's supposed to count. But we know that at least from just looking at this, we still need some kind of bounding cochains and so on. So let's keep in mind that they are there. But for dimensional reasons, so we know the red chords, there are these A, B, C, so they have degrees 0, 1, and 2. And the dimension of such a curve is just the sum of degrees of its positive punctures. So therefore, in fact, what you will find here when you take the rigid part is just exactly those which have only degree 0 positive punctures. So it's a simplification. And we write this potential, so it's a complicated thing, but we sort of think of the F0 part, which is the ones which have no positive punctures inside. We're in non-exact situation, so we're in the coniform, right? So there can be such things. So there is the F0 part, no positive puncture, F1, 1 positive, and so on. And then there somehow is the lower part in this boundary, and the upper part is called Hamiltonian in this business, and it should count corresponding one-parameter families of curves at infinity. So remember, there is always this R translation. So, so now, what would be if we manage to overcome this boundary splitting problem? Then what would be somehow the structure of this theory? Well, it would be that you have the one-dimensional curve is some curve like this at infinity, and then there can be many curves attached here in various ways. So, so what I'm here kind of trying to indicate is that I take so this is the Hamiltonian, and then I act on that on e to the f. So f is the count of all connected curves. So e to the f means I take all these connected things, so like this. And then I get a lot of stuff that's just hanging loose as usual. So if I want to go back, I will multiply by e to the minus f, take them all out. So, and then if that's really the boundary of a one-dimensional moduli space, then what we find is that this equation is actually 0. And so, I mean, e to the minus f invertible. So this is sort of our basic equation, which corresponds to the augmentation equation in some sense. So, but let's look again at the fact that we have very special curves. So when this moduli space should be of total dimension 1, that means that all of these positive punctures have degree 0 except one which have degree 1, right? So you can have 2 or anything else. So it's somehow just only these simple combinations that can contribute. So then, let's now look at what is the counterpart. So imagine that we managed to do this. So we have inside, maybe I can still go here. So before we had this disk and we had its bounding cochain, right? It's called a sigma. And then we had some other disk intersecting it on the boundary, and we needed to count insertions of this disk, right? And that led us to this P. So that we somehow insert this dw dx, right? That was the key thing. But now, what is the counterpart in higher genus? Well, you know, it's easier if you imagine you have two such things. So what you can do is you can attach the disk, you know, once at this point. You can attach it at this point and that point, but you can also use things that somehow, you know, become higher genus. So where you attach it at both points, right? And so on. And if you think about it for a little bit, then this count, if you take this e to the gs ddx, acting on e to the f, you know, that counts exactly up to multiplying by e to the f too many times, count exactly such insertion. So this one can act either, you know, on the f or on the f in front. So this somehow is on the f in front, and the other one is when you act on the f. So basically, if we can make this happen with this obstruction cochains, it says that in the Hamiltonian, we should make the substitution p is gs ddx. So this is some kind of, I don't know, some kind of string theory derivation of high school quantum mechanics or something like that. But anyway, so that's what we should do. So from just these formal things, an analogy with what we did for this should be the structure of the theory. So finally note that when we wrote all these curves, the curves that have no positive puncture, they are kind of our old friends, right? So they are the curves which which have a boundary on this LK and nothing else. So when we take this function, that's exactly is the wave function for this, counting curves ending on LK.
Tobias, can I ask, is there anything special about knots here? I mean, can you do this in any arbitrary mirror symmetry setup? Always introduce this quantization? So to speak by higher genus?
I mean, it is of course supposed to work, but I have a hard time making it work here. So in some sense, it shouldn't be too special. There are a couple of features that I would need. For example, that the infinity generates homology of the filling and so on. But there should be a general story, at least in dimension 3. So I'll tell you how I, try to do it. But I cannot claim I really can do it. But it should work.
What is special about dimension 3?
The way that I overcome the boundary splitting. So I'll show you. So maybe there is some analog, but it will work slightly differently, I think, in higher dimensions. But okay. So it's okay. So now,
is there like a sort of degree? I mean, dimension 3 means the boundary is like 2 Calabi-Yau. Is there sort of a degree issue in other?
Yeah, there would be a difference with degrees and then dimension and so on. So that's something. It's a kind of great thing that everything is rigid. It makes life easier in some sense. Or maybe harder, but it's different than other things. So, okay. So what we have is this equation, which is not there, but our main equation that will come out from this is this h e to the f is equal to 0. And now, just like before, this e to the f involves not just f0. If it was just f0, imagine you have no, so it actually happens for the unknown. So imagine that you have no curves at all on top with negative punctures. Then this equation itself would be just an operator equation. It's kind of Schrödinger equation, so there would be an operator equation for the function that we kind of it's the Humphrey function that we're really after. But now it's not the case, because we have a lot of terms which involve auxiliary positive punctures. And so we would like and positive and negative, so kind of just like before, H has such terms acting on these positive functions. So somehow what we would like to do is we would like to eliminate those from this equation and get an equation just for e to the f node, and that would be an operator equation, because we already know that we somehow have this by a substitution in the Hamiltonian. And this should be the recursion relation, in this case, for the colored Humphrey. So it's known, I think, by Garfalides and somebody that this colored Humphrey is Q holonomic, it's called. So there should exist such a differential equation, and that's where it should come. Okay. So, basically what I'm saying is that if we can define this theory, then we get, in some sense, a quantization of the augmentation polynomial, right? So, because if you let them commute, and then that just means that you look at only disks here, so that would be exactly, in some sense, the augmentation polynomial. So if this SFT exists, then it does quantize the thing that we would like. Yeah.
So e to the f0 is the color Humphrey.
That's right.
Did you say that?
Yeah, but I changed the notation for it. So there was this string partition function, right? Initially it was in T star S3, and then we did the transition, and then it appears like this F0, e to the F0. Okay. Now, to work, so I want to try to sketch, and this of course has not been done, and then it is related, I think, to work that Foucault is doing, and so on. But let me at least I will show where there are some difficulties and what one would need to prove. So, we look at the degree 1 and 0 ray, of course, because that's all we need to be interested in by these dimension considerations. And then we need some additional data to define this thing, and that's this is what we kind of put in, and you can see, you know, in general for which Lagrangians you have such things and so on, and similar things should work. So we fix a Morse function on LK, which basically will allow us to build these obstruction code chains in a more dynamical way. So basically we have our boundary of a homomorphic curve, and then we have this Morse function which flows off towards infinity, and we take all the flow lines starting on the boundary and then going off to infinity. So that should give us our kind of boundary code chains. But we need a little bit more because of some boundary splitting phenomena that I will show you in a second. So we also fix a 4 chain which has boundary LK or twice LK, and we want it to look like the multiplication of this gradient of f by the complex structure near the boundary, right? So along LK. So basically what we're doing is we're implementing a slightly tiny little bit of real algebraic geometry here. So basically what you should think of is you should think of having R3. We have R3 inside C3, and then then it's just so you have some vector field in R3, and now you're just multiplying it by I, so you get the sort of beginning of a 4 chain which bounds R3. Okay. And then you'll see in a second where it's used. So now we look at the
Bounded twice,
yeah, just like yeah. You need it to yeah.
Ah, okay.
From both sides, right? So it's somehow yeah.
Wouldn't that make it a cycle? Bouncing from both sides.
It's not quite a cycle, right?
So somehow the orientation.
So there is a very, I'm not going to tell you, so this of course was not fantasized only about in this setup, so it comes from some old work I did in following the law in real algebraic knot theory. So there you can make sense out of certain self-linking numbers by choosing a certain chain bounding RP3 in CP3. So this is a kind of mimic of that. But let me anyway show you the pictures. So now, what are the problems here? So the problems are basically all related to boundary splitting. So here's a picture of this boundary splitting that we know before how to kind of resolve. So in the case of the disk. And now, we should also resolve it. So, so you know, so this was the thing that you start with 2 disks that do not intersect, and then they now intersect, and then you can somehow glue them up, right? So that was the thing. And the key was before that. So what happened before? So let me draw the boundaries of the disks. Before. So on this side, you know, you have 2 disks, and then they collide in the middle. And now on this side, the 2 disks, if you think of deforming complex structure or something. So you have 2, you deform, they intersect, you go over to here. Now you can glue them. So you have 2, but you now have 3 disks, right? So somehow this 2 equals 3 we don't really like. So what I'm suggesting with the bounding cochain is that we're now also counting a graph like this, right? where one boundary intersects the bounding cochain of the other one. Right? So now we're counting 3 here, and we're counting 3 here. So the linking number changed and the number of these changed. So that's the key idea. So we would now like to do the similar thing, but now in higher genus. And in higher genus, it's somehow slightly more complicated because here you can glue many times. And what the claim is that this thing should somehow contribute basically e to the linking number times this gs times this thing. So that's a bold statement. It needs proof, and there is a kind of indication of proof here, but I can't say I can prove it. So this is one of the things that should allow us to overcome the boundary splitting. The same as before, but we need to understand what happens when we have all these constant higher genus curves involved. So the other thing that can now happen, and which explains the use of this 4 chain. So there are 2 versions of it, this version and that version. So in the first version, what we see is a holomorphic curve with boundary on the 0 section, and this boundary component shrinks, right? It can shrink to a point. And then you see another holomorphic curve intersecting the 0 section at one point, and you would like the counts to agree. So when it moves on, it will have an intersection point with this reference 4 chain, right? So 2, which is the dimension of the holomorphic curve, plus 4 is equal to 6, so there it's 6. So you can again somehow see this one counted as a formal holomorphic curve, which has this point inserted in the chain. And then and again, there is a similar thing that when you do this, you use several copies of the chain to glue. So you actually open up many holes here. So it's again some kind of e to the number, intersection number, similar thing like here. And for example, to see that has to be the case is shown in this picture. So and that's why I sort of know something about this. So this is what happened in real algebraic knot theory. So when you try to define this chain by flowing with the Morse flow up, then of course at points you become tangent to the flow. But what then happens? So if this was a real algebraic curve, then you have a double point, and after this thing you don't have a double point, but you have a complex double point, a kind of pure imaginary double point, and this is a remnant of that. So somehow this linking information to counting into the GS is related to this point, which is a point in the holomorphic curve intersecting the 4 chain, and it should also then be counted like e to the GS times intersection number with this chain.
So is that the same thing that string co-bracket, you have this self-intersection goes to, I mean a string for co-bracket,
Yes.
there's a phenomenon that there is some self-intersections and whose 2 points just collide. I mean,
I think in some sense it is probably the same. I think so, yes. I think it's but kind of in this case, right?
yeah, it's something as a reason that you need to remove this constant cut strings.
Yes.
Define co-bracket.
Yes, it's something like this, I think, yes. But I should again emphasize that I don't really know. I mean, this is very much a sketch, but the hope is that from knowing that the theory exists and the fact so if we're lucky now, what did we see? So we saw that somehow the holomorphic curves that we're supposed to count, they're holomorphic curves, and then some kind of linking numbers with components. So maybe on the next picture I have something like that. So this is indicating what thing our f should count. So it should count some kind of graphs where at the vertices sits curves, and at edges there sits some kind of linking information insertion like that, and possibly some kind of intersection with this chain. So it's a big mess, but we're never in this theory really going to count it, because we're going to do the count at infinity. And at infinity, it's not at all. So this was the structure. Maybe I'll skip here. I'll keep the picture. So at infinity, it's not at all so bad. So because at infinity, you can make sure that there are no basically, you know, we saw the unknot at infinity, and there were some disks, but there were no serious higher genus curves. So all of them you can show if you set it up correctly. So there's some kind of, you know, need to do a little bit of this dipping trick, as it's called. But you can basically make no actual higher genus curves at infinity, and therefore you have some disks that you can actually draw, and you need to keep track of the linking information. So this is slightly shady. There's some kind of problematic things coming from multiply covered trivial strips that you need to figure out, and I haven't. So in some cases you can do without that, but in general you cannot. So, but it's a very limited set of problems that you should be able to solve. So the idea is that maybe you can actually compute this H. And that would be pretending, or if you, once you can define the theory, then you would then be in business, right? So this is repetition of what I said. And let's see, so how far we got so far. So for the unknot, unknot is great, so there's nothing else to check. So you have no linking, nothing. It's just it's just a natural lift of the equation to higher genus, and this coincides with the calculations of this recursion relation for the Hopf link. And then you can do the Hopf link, and the Hopf link, you know, you get somewhat. So here I somehow the DDA12, and that's the negative punctures of the disks on top, and then this means that there are at least one or so positive punctures. But the key is that a very small piece of these Hamiltonians, I'm not counting so much, it's just a couple of degree 1 quarts, it actually allows you to do the elimination theory, and for the Hopf link, so I'm not, you know, you don't have to look into any of these formulas, but the key basis is just that for the Hopf link, the answers matches what you get from the Hopf link.
Well, what is the statement about you only need finite amount of this this operator?
Yeah, so you have this, so as I said, you have this h times e to the f, right?
Yeah.
And that, you want to do elimination theory on that to get the equation for e to the f naught. So you need to remove all the all the auxiliary a's. And so if I go back to one side, so somehow you need to remove these guys from the equation, right?
Which guy?
These ones, so that they correspond to holomorphic curves with negative punctures, for example. So you really would like to have just insertions.
Okay.
And so you need to do some elimination theory to take those away. And you have a long list of equations here.
Okay.
But sometimes when you do elimination theory, just a couple of them is enough. So there are huge dependencies in these equations in some sense. So therefore you just need to do a couple of them, and then you can...
Is this somehow empirical observation? Is there some sort of...
It's empirical observation, but I will offer some kind of explanation of why there should be a solution, I think. Because I don't know, maybe somebody knows about this elimination theory in non-commutative variables, but I don't. So I will prove something in some different way very soon. Okay, okay, it means let's forget about details, but here is something slightly interesting. So this is the trefoil. And again, from not so many equations, we can get the answer to match what it should be, and it's of course reassuring thing. So it's a much longer equation than what you have when you don't have the non-commutativity. So it's positive. But here something furthermore interesting appears. So these things were calculated, I think maybe by Ekholm and somebody. And there appears, so when you take the limit, you get the augmentation polynomial of the trefoil, but you also get some junk. So, but in fact, this framework offers some explanation for the junk terms. Namely, when you do elimination theory in these non-commutative variables, sometimes you have to change orders. You know, f times g has to be g times f, and then you pay a price. And that's where all these kind of junk terms come from. So you wouldn't, I mean, that means that it doesn't quite commute, right? you know, because you know, if you take GS to 0 in H, you should get the right equations and then do elimination theory. But if you do elimination theory first and then take GS to 0, you don't necessarily get exactly the same thing. So it seems to be working. Okay. Yeah. So now I would like to come to the last topic of this series, and that's somehow along with Vivek's question. So how can we actually say that, you know, there exists a solution of these equations and so on? And what I would like to say here is that we can actually compute this e to the f0 from knowledge of H in some kind of way. So I call it topological recursion because basically H is computed from disk things with a little bit of input, linking numbers. And then with that information you should be able to now recover all the curves inside if we believe that this framework works. So, and let me try to explain that. So the main, so in some sense, what happens is that we have this.
Why is H computed using only disks?
So at infinity, for this lambda k, we basically have pretty good knowledge of these holomorphic curves, and there are some. They all kind of limit to disks on the unknown, and on the unknown you can check there are only disks. So then, yeah. So let me say where. So you have. So you have this. This is sort of this. The Lagrangian of the unknown, and then you have some other Lagrangian lambda k sitting right next to it. And then you crush it down to lambda k, and so holomorphic curves on lambda k has to limit to holomorphic curves on lambda u. And that means that you can describe them all by basically some holomorphic curves on lambda u. But there you know that they are all disks. And then these gradient flow lines, and what you're really afraid of now, kind of this thing. But when you think, even if you see such a thing in the picture, then for it to become an annulus, when you lift it to the symplectization, the area of this one has to match certain height. And in this case, the area is basically 0, so you need to fight flow lines which begin and end on the disk and end at the same height. And you can do it in some sense explicitly by putting sufficiently many maxima and minima. It's not so many actually. So that's the argument. Okay. So our first observation is what Kenny was talking about last time, that in fact by our we get the disk potential or its derivative by solving the algebraic equation. So we know it's an analytic function. And so in some sense, when we take the limit into the exact situation, when we go to cotangent one, we can view it's a small perturbation. So it goes to 0 and it's a small perturbation of what we have. So now what we are going to do is we're going to look at the augmentation curve. So it's complicated, but if I take a point here, I have my augmentation, and this augmentation allows me to linearize the differential. So I can look at what's called this linearized contact homology, which is just like counting now strips, but my strips, I have to allow some things like this. So that's what the augmentation does, so it makes the ordinary square homology work. And now, what we can say is that in the classical situation, so when we go to T star S3 or R3, then we can actually, maybe S3 especially, then we can actually calculate this linearized homology basically by the same, this is a sort of standard isomorphism map. And we use spectral sequence and you have the isomorphism disks. And in this case what happens is it looks a little bit strange because we're basically looking at the space of paths from the knot to itself. And it should maybe not be completely zero, but remember that we're actually looking at twisted coefficients where we have the e to the x variables in there. So that kills off most of the homology. So, you know, if you take a torus with the general local system, it doesn't have very much homology. But here a little bit of it survives, so we can say that for generic, or actually for non-zero x, I guess here, we have rank 1 in degree 1, rank 1 in degree 2, and nothing in degree 0. So it's a very simple homology. And by our result about the Romo with potentials, the same thing will hold true for a small perturbation, right? When we're near, when Q is small, then this will go. So, and somehow if you, so in a neighborhood of, in this curve, we have the same type of behavior. Okay. And moreover, we can actually look into these maps a little bit and say that the generator here actually needs to kill off the thing over there. So that means that when I look at the moduli space of holomorphic curves, holomorphic disks, passing through my reference curve psi, so that was the one where all the obstruction chains end, then actually it has to be a non-zero count of such curves. So that's a somehow it's psi, and when I look at the generator, it has to hit that because it is somehow whole thing is a sequence. Okay. And that also persists on the small perturbation. So now this allows us to carry on and actually calculate all the amplitudes inside. So this was the thing statement. We pretend that we know, or after calculating these and linking numbers, we know everything about infinity. And then we go on. Maybe it's better to go the first step on this thing. So basically from previous calculation we know about the disk, right? So that's what the augmentation gave us. So now let's try to calculate some annuals. So what I'm suggesting is that we take this type of, we look at the moduli space of annuli. So here it's some kind of induction, so we have a more complicated curve. But we look at the moduli space of annuli with a positive puncture this big. And then we see, you know, what can be the boundary of this space. So, well, we can break like this. So now this is dimension 0 and this is dimension 1. We can also break in some sense like this, where we have this again dimension 0, and this is now insertion. Insertion on the boundary. And we can break like this. So yeah, I shouldn't have started with the angles. I'm sorry. So now let's see what happens. So if I start with B being the generator in this linearized homology, I know that this term is actually gone because it's a cycle. So there's nothing here. So and if I knew, so and this guy is at infinity, I know it. So then I can see in my pictures, I know it, and assume that I know this guy. I'll tell you how I know it in a second. But assume if I know it, then you see what we have here. Here we're counting the holomorphic disks with a positive puncture at B ending at this kind of with an insertion, and we know from this previous result that it is a non-zero count. So it's a non-zero coefficient. This thing is a non-zero coefficient times the annulus equal to something I know. So then I'm done. I managed to calculate the annulus. So we need to calculate this thing. And note here these are degree 0 things. And in degree 0, I know that the homology is trivial. So I can pick a primitive B prime of A, so that the count of these things exactly is 1. I glue it, and the boundary looks, somewhat similar. There is some other such configuration which is more or less the same. But then I have the curve at infinity as the last thing. So again, I would actually this doesn't. Sorry, it's just like that. So again, the fact that I have no 0 degree homology allows me to calculate these things. Now I go on to the next genus. So again, I would have this splitting like that. I also need to use this argument first to calculate annulus with any number of, with one. I actually count the number of positive plus the genus or something like that. So I go on with this argument, count annulus with one puncture, and then the next time it's something again like this. This is the disk and the most complicated curve, and I can solve it recursively. So in some sense, this is supposed to indicate that I mean, this I guess you cannot quite do, but I think it proves that the other equation has a, that you can do the eliminations with it. Okay. Yeah, that's more or less what I said. So okay, so then you can imagine you can soup this up to higher or lower, or you can. So I should stop it. Thank you so much.
Are there any questions or comments?
So this last few minutes was some sort of finite determinacy discussion?
The last few minutes was some kind of proof that if you know, if you have this theory, the SFT, and you know the curves at infinity that you're supposed to, by counting some linking numbers, then you can actually determine the wave function, this e to the f norm, from that data. Right?
Let me ask a slightly different question.
Yes.
Can I restate whatever this discussion was as saying something like you constructed some sort of infinite family of differential equations that thing has to satisfy?
Yeah.
Because like moving these, that's the nature of this argument.
Yeah. I mean, I'm constructing the solution. I mean, so I'm after a D module, and I'm constructing a generator. Right? So whether that is finite determinacy or not, probably not. But I don't know. Maybe it is.
Yeah, I don't know.
Yeah. But that's so I'm sort of constructing the wave function, right? And I should say that these, of course, for links and all these things, it works equally well. So
I mean, you're somehow constructing it by saying, you know a certain number of terms so you can compute them, and then you try and find the other terms.
Yeah.
But can I say this procedure in terms of certain relations among the terms, and can I say that procedure in terms of an operator which annihilates it?
Yeah. I mean, I'm somehow. I guess I'm somehow. I don't know exactly how to formulate it, but indeed you're using sort of, term by term, this h that I have, right, which has some kind of extra negative punctures. And I think that the point is that this condition of the linearized homology shows you that you can actually continue this story. So you have some kind of, maybe somebody knows something.
What was the condition?
So I'm computing a little bit this linearized homology for the. So it's like the, I don't know, whatever tangent space of this calculation or something. So I know that I have near, in a neighborhood of this point in the augmentation variety, I have these, the linearized homology looks like that. And this is what somehow drives, I mean this you can forget about, but this is what somehow drives for me the recursion. So it tells you that you can solve certain equations, you find sort of primitives of these guys that you want to eliminate, you put them and then you do something and you get to things you know before. So that's somehow it's the key. So in some sense I think that this proves that on the linear level, when you just have one puncture and so on, you can somehow lift degree 0 guys to degree 1 guys, and then when you degenerate, you know it can only split into simpler pieces. Yeah, so that's the nature of the recursion. I don't know what this is really, but maybe somebody else knows.
This is, is this the tangent space to the augmentation variety, or what is the?
Yeah, in some sense, or it's rather the. Well, is this the tangent space? No. I mean, there is a certainly kind of like a shape over the augmentation variety, which consists of these linearized homologies, right?
No, it's a tangent space.
It's a linear, yeah. If you linearize the equation for epsilon, I think it's.
So what it's saying is basically that it's smooth.
It's smooth.
There's no multiplicities.
It's smooth, yeah, I mean, at the generic point.
A generic, which is not true because
Yeah,
the
yeah.
scheme is
It's a
reduced scheme a generic.
Yes, that's right. That's exactly it. That's right. So indeed, if you linearize the augmentation equation, you get this. So yes.
So the recursion argument is perturbative in nature. It's perturbative in
AGS.
GS.
Yes.
Can you repeat again how do you understand the fact that in the end H depends not polynomial in GS but on each of the GS, on Q?
Yeah, so
is this
right.
true under some conditions?
Yeah,
Is the-
no, this should, I think, always be true, because somehow, so the way you set it up is that the terms, so this, this H that we're looking at, right, it's sitting at infinity. So what it really looks like is some kind of holomorphic disk, and we can sort of assure that there are no more complicated things than disks at infinity. So then, but that's not all the curves. So some of them are formal. So the only thing we need to do is we need to take the disk and then basically see on the boundary how it links itself. But each such linking, when it's formal, contributes something like e to the gs.
So it's just some ordering.
Because it's some kind of ordering, and it corresponds to that the thing that could happen when you destroy is that it starts intersecting itself. And the theorem that, of course, I quite haven't proved, but should be proved, is that when you have this crossing, then the contribution is the change is this is somehow the counter curve on the other side when you pass the cross. And so that's the whole. If you can prove that, then you would know that this really is in terms of e to the gs rather than gs. So that allows you to put all this in a nice, very nice package.
Okay, maybe we should thank the speaker again. And we have a 20-minute